All right, welcome to the Explainer. Today, we're jumping into one of the absolute cornerstones of chemistry, balancing chemical equations. Seriously, if you've ever wondered how scientists can predict exactly what happens in a reaction, well, it all starts right here. Let's get to it.
So here's what we're going to cover. First, we'll talk about chemistry's golden rule, the big why. Then we'll get into the rules of the game. After that, we'll actually balance an equation together step by step. I'll even share some pro tips to help you avoid common traps. And finally, we'll wrap up with why all of this really matters.
Okay, let's start at the beginning, chemistry's golden rule. Before we even think about changing numbers around, we have to understand the one single principle that forces us to do this in the first place.
This right here, this is everything. It's the law of conservation of mass. It's one of those fundamental truths of the universe. It just means that whatever stuff you start with, you have to end with the same amount of stuff. It might look different, but it's all still there.
So when you think about a chemical reaction, don't picture magic. Picture a reshuffle. You have your starting materials, the reactants. The reaction is just the process of breaking their bonds and rearranging those exact same atoms into new combinations, the products. No atom gets left behind. They just find new partners to dance with. I love this analogy. Imagine atoms are like Legos. On the reactant side, you've built a house. The reaction comes along and you carefully take that house apart piece by piece. Then, using those exact same pieces, you build something new, like an airplane. You didn't create new bricks or lose any old ones, you just rebuilt. That's all a chemical reaction is. All right, if we're just rearranging blocks, there have to be some rules, right? You can't just do whatever you want. So let's move on and learn the most important rule of this whole balancing act. And this is it, the big one. You have two kinds of numbers to deal with. First, there are the big numbers you can write in front of a molecule. Those are coefficients. They're your tools. They tell you how many of that entire molecule you're using. You can change these all you want. But then you have the small numbers inside the molecular formula. These are subscripts. And the rule is simple. You do not touch the subscripts. They are sacred.
It's a totally fair question, though. I mean, if you need another oxygen atom on one side, why can't you just change H2O to H2O2? Seems like an easy fix, right?
Well, here's exactly why not. Because the second you change that subscript, you've changed the fundamental identity of the substance. H2O is the water you drink. Change that little subscript by 1, and you get H2O2, which is hydrogen peroxide, something you definitely do not want to drink. You're not adding more water. You're creating a totally different new building block. And that's cheating. Okay, we've got the why, we've got the rules. Now it's time to actually get our hands dirty. Let's walk through an unbalanced or skeletal equation and bring it into balance together.
So here's our puzzle for today. We have iron reacting with water, and it's making some iron oxide and hydrogen gas. Right now, this equation tells us what's in the reaction, but it doesn't tell us the correct recipe. It's not balanced.
The very first thing we always do is take inventory. Let's count them up. On the left side, the reactants, we have 1 iron, 2 hydrogens, and 1 oxygen. Now look at the right side, the products. 3 irons, 2 hydrogens, and 4 oxygens. Whoa! See the problem? You can't start with 1 iron and end with 3. The universe doesn't work that way. This is what we need to fix. Okay, a good tip is to start with the most complicated-looking molecule, which here is Fe3O4. Let's focus on the oxygen. We have 4 on the right, but only 1 on the left. To fix that, we need to put a big 4 coefficient in front of the H2O. Boom! Now we have 4 oxygens on the left. Perfect. But notice what happened? That also gave us 4 times 2, or 8 hydrogens. We fixed one problem but created another. That's totally normal, just part of the process. No worries. Let's tackle that hydrogen imbalance now. We have 8 hydrogens on the left, but only 2 on the right. So what times 2 equals 8? 4! We'll put a 4 coefficient in front of the H2 on the right side. And just like that, our hydrogens are balanced, 8 and 8. Oxygen is still good, 4 and 4. We are so close now. All right, the very last piece of the puzzle is iron. This is why we save the single elements for last. They're so easy to fix. We have 3 irons on the right and just 1 lonely iron on the left. So the fix is obvious, right? We just put a 3 in front of the Fe. Now look at that table. 3 irons, 8 hydrogens, 4 oxygens on both sides. It's perfect.
And we are done. We have a beautifully balanced equation. 3 iron atoms plus 4 water molecules react to form 1 molecule of iron oxide and 4 molecules of hydrogen gas. Every single atom that went into the reaction has been accounted for coming out. Nothing created, nothing destroyed, just rearranged.
So that method works great, but let's talk about a few extra tricks and strategies that can really level up your balancing game and make you a whole lot faster.
So, to recap some key strategies, always save those lone wolf elements, the ones all by themselves like our Fe, for the very end. They're the easiest final tweak. Also, it helps to start with elements that only show up in one place on each side. But the biggest tip of all, when you think you're finished, do one last inventory check, just to be sure. It takes 10 seconds and can save you from simple mistakes.
Now, here's a super cool trick for when you get really stuck. Let's say you need 7 oxygen atoms, but it only comes in pairs as O2. What do? Well, you can kind of cheat for a moment. Just use a fraction. Write 7/2 as the coefficient. I know it looks illegal, but hang on. Once everything else is balanced, you just multiply the entire equation by whatever that bottom number is. In this case, 2. And like magic, the fraction disappears, everything doubles, and you're left with clean, whole numbers. It's a lifesaver.
So we've gone through the how-to, but let's take a step back and talk about the so what. Why do we even bother with all this? How does this move from the textbook page to the real world?
Look, this isn't just a puzzle to solve for homework. Balancing equations is the language chemists use to describe reality. It's the absolute foundation for something called stoichiometry, which is the math that lets us predict exactly how much stuff a reaction will make. If you work in a lab, this isn't just important, it's everything.
So in the end, balancing an equation is about respecting that fundamental law of the universe, that matter is conserved. It's about making sure every single atom is accounted for, allowing us to turn chemical chaos into a predictable, understandable process. Now you know the rules, and you've seen how it's done. So the only question left is, what will you balance next?